Okay, you guys, we're starting a new chapter with 2.1, and 2.1, we're going to be describing location in a distribution. So where things fall in a distribution of data. So biggest things to take away from today. After today, you'll be able to find and interpret the percentile of an individual value within a distribution of data. You have heard about percentiles before, and actually people use them wrong a lot of the time. They'll say that they are in the 99th percentile when technically they should say at. So for here, don't say in, say at, because we are talking about a location. That's where that score is at. If you haven't heard about percentiles, the best example I can give to you is, and maybe this will make sense to you later in your life, but when people have children and they are babies, they have lots of doctor visits, and every doctor visit, you will get your height, not yours, but the baby will get its height, weight, and head size measured, and then they compare it to other babies that are at that age. And so, for example, my son, okay, would be his height and weight would always be, his height would be like the 70th percentile, so meaning that his height was bigger than 70% of the data that they had, or the 70% of the entries that they had. Okay, but then his head size, because he had a big noggin, would be at the 99th percentile, meaning that he was higher. His head measurement was greater than 99% of the other babies at his age. So, another thing that they use percentiles in a lot is test scores, ACT, AP test scores. That's kind of how they score some of those things anyway. So we're going to learn about percentiles. We're going to figure out exactly what percentiles are, but we're also going to estimate percentiles and individual values using a cumulative relative frequency graph, which can be helpful. This next thing we're going to do is we're going to learn about z-scores. And z-scores kind of give us some more information on location in a distribution. And then the last thing we're going to do is we're going to describe the effect of adding, subtracting, multiplying, or dividing a constant to the data. What happens to the shape, center, spread, and distribution of it. So, first thing we're going to talk about are percentiles. And it says the pth percentile of a distribution is the value with p% of the observations less than that. So here's our example. We've got a bunch of test scores, and Jenny earned an 86 on her test. That puts her right here in the data. Okay, how did she perform relative to the rest of the class? Well, if we didn't have this lovely explanation right here, what we would have to do is figure out, one, how many test scores there are. So we count them all up, and when you count them all up, you have a total of 25. Okay, then we look to see how many scores are lower than Jenny's. So all these red ones, if you look at the red ones that are lower, okay, there are 21 scores that are lower than Jenny's. So if we did 21 divided by 25, or find out what percent that is, that's how we get 84. So we would say that Jenny is at the 84th percentile in the class test score distribution. Being really careful to not say in, but to say at. Okay? So we're going to do some practice problems real quick. Same test scores, we're going to find the percentiles for the following student. So Norman, who's earned a 72. If I'm looking at my STEM, okay, got to remember there are 25 total again. 72 is right here. Looking, there is only one score lower than Norman's out of the 25. And we grab our calculator to find that percent if you need to. If your brain is working better than mine, you wouldn't need to. Okay, multiply by 100, and we get 4%. So we would say Norman is at the excuse me at the 4th percentile of his class test scores. That would be the statistically correct way of writing and justifying your answer on that one. Okay? We move on. We go to the next one. Katie. We're going to talk about Katie. Katie, who scored a 93. Katie's 93 is right there. Okay? And if we notice, she's test number 25. So that means that there are 24 scores underneath Katie. Okay? And then when we do that, 24 divided by 25, we get 96% or 0.96, which is 96%, which then would say that she falls at the 96th percentile. 96th percentile. So something we should recognize here with Katie, even though she was the very, very top, there's no such thing as the 100th percentile. Okay? Highest could be 99. Okay, but the bigger your sample size, the closer to 99 you're going to get if you're the very, very top. Okay? There's two students who earned scores of 80. That would be these two students. Okay? Although they are the same, technically we're going to go for the upper one, which would mean that there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 scores lower. So 12 are lower than that 80. So 12 out of 25 would give us a, drumroll please, 48%, which then tells that they are in the 48th percentile. Awesome. Okay, so that's the next thing we're going to talk about are cumulative relative frequency graphs. So biggest thing to know is a cumulative relative frequency graph displays the cumulative relative frequency of each class of a frequency distribution. So that's kind of a lot of words, but basically what it is it almost graphs percentiles, if that makes sense. Okay, so we are going to find the relative frequency, the cumulative frequency, and the cumulative relative frequency. So, relative frequency, we are going to take the total frequency, okay, and then divide it by the total. There are, if we add these up, 2, 7, 13, 22, 73, that is 44 total, okay, and of that 44, we're going to do some major calculator work here. We're going to figure out the relative frequency. So this would be 2 out of 44, 7 out of 44, 13 out of 44, 12 out of 44, 7 out of 44, and 3 out of 44. So when you get your calculator going and you start finding all of those percents, you end up getting, let's change it, you end up getting 4.5%, 15.9%, 29.5%, 27.3%, 15.9% again, and then 6.8%. 6.8%. Okay? That's the relative frequency of the presidents. We're talking about presidents and their age. So from the 40 to 44 age, there are 2. So that's 4.5%. Now we're going to do the cumulative frequency, and that means everything from there and below. So this one, when we start, it doesn't change. We're still at 2. Okay? But then the next level, we're at 9 because 2 plus 7 is 9. And then we add 13, and that's 21. And then we keep going, and we get 34. Wow. 9 plus 13 is not 21. Sorry. Sick brain. 9 plus 13 is 22. Then we add 12, and we get 34. Then we add 7, we're at 41. And then we're at 44. So the cumulative relative frequency is the same thing we did with the relative relative frequency except for we use our cumulative numbers. So this time this would be same thing, 2 out of 44, which is 4.5%. Okay, but then we would use the 9 out of 44, which is going to give us 20.5%. Okay, and then the 22 out of 44, that's exactly 50%. And we continue this process, okay, and when we're done, we should end up at 100. So we get 77.3%, 41 out of 44, okay, is 93.2%, and then 44 out of 44 is 100. Okay, at any time, feel free to pause the video if you want to crank this out yourself or work through it to check my math. That's totally okay. But once you have the cumulative relative frequency evaluated, then what we do is we plot the points for a graph, okay, making our axes the two things. One's going to be frequency and one's going to be age, okay? And then a couple of things. We're always going to start our axis with 0 and end at 100% on the frequency because that's where we start and where we end. Then we're going to plot the points and connect the dots. So you have a part on your paper, on your notes, that has a little axis created for you. I want you to take some time right now to plot the points. Okay, so pause the video because then I'm going to put the graph up here in a second. But pause the video, try to plot the points and see if you can understand what that graph is supposed to look like. And if you need to cheat, then wait a second, the graph will pop up, and then pause the video so you can create your graph. Okay? Okay, so here's what your graph should look like. If you notice your distribution, okay, your cumulative relative frequency, by the time you're done, it has all of the data underneath it, and that's all it's talking about. So it's kind of very similar to percentiles, is it has all of the data underneath it. And so when you get to the top, you have 100% of the data, or 99% of the data underneath it. Okay? Okay, so the next way that we can measure location is this thing called z-scores, or measuring position. And a z-score tells us how many standard deviations from the mean an observation falls and in what direction. Okay, so the way it does that is we have this equation. So I'll write this down. It says z, or the standardized score, okay, is x minus the mean, or with x being what you're trying to describe the location of. Okay, so that's the data point, the exact value you're looking for. Okay, we subtract the mean and then divide by the standard deviation. And if that's negative, that means that it's to the left, okay, of the mean, that many standard deviations to the left. And if it's positive, it's that many standard deviations to the right. So we're going to do some practice. Okay, I'm going back to these test scores with Jenny and her classmates. Okay, the class mean is 80 and the standard deviation is 6.07. What are the z-scores for the following students? Jenny earned an 86 on her test. So the first thing we're going to do, okay, is we are going to go 86 minus the mean, which is 80, all over the standard deviation of 6.07. So if we remember, it's x minus mean all over standard deviation. That's what our z-score is. Okay, so grab a calculator, do 86 divided by 80, we get 6, which then leads to 6 over 6.07, and that is a z-score of 0.99. This would mean that Jenny's test score is 0.99 standard deviations above the mean score of the class. Okay, that's what that z-score would mean. Z equals 0.99. Okay, Feel free to pause the video and try B and C on your own, and then I'll go through them real quick and check to see how we're doing. Okay, moving on to Kate. Kate scored a 93, so we take her score, that observation, 93, minus the mean of 80, divide it by 6.07. And what we end up getting is once we're all done, 2.14, okay? Which means, in other words, Katie's result is 2.14 standard deviations above the mean score for the test, okay? 2.14 standard deviations above the mean for test scores. Okay. And then the last one, Norman. We're going to talk about Norman. And when we do Norman's, you're going to notice something different. We do 72, his observation minus the mean over standard deviation. When we plug that in, we get negative 1.32. So a z equaling negative 1.32 would imply that Norman's test score is 1.32 standard deviations below the mean test scores. Okay? Okay, so the last thing we're going to talk about today now is transforming data. Okay, and what we're talking about when we're talking about that is transforming converts the original observations from the original units of measurement to another scale. So think of it like meters to feet, or Fahrenheit to Celsius, or whatever, years to days, months, whatever. That happens often because it's more relevant um, for what you're talking about. Maybe you want to know seconds instead of hours, or something like that. But transformations can affect the shape, center, and spread of a distribution. So we're going to look at this example. Okay. In this example, it says, soon after the metric system was introduced in Australia, a group of students was asked to guess the width of their classroom to the nearest meter. Here are their guesses in order from highest to lowest. Okay. There's a lot of guesses, but if you look at my dot plot, okay, it shows you the distribution of the guesses. And I think we would be very similar. I don't think we would maybe know exactly. We're not very good at the metric system. So here's what I want you to do. I'm going to give you some information. I'm going to give you the numerical summaries of this distribution. And I want you to pause the video, okay? And I want you to identify a couple things. I want you to identify the shape, the best representative of the center, how we should do the spread, and potentially any outliers on your paper. I've left some marks for you right there, okay, to see if you can best describe this data, okay? And then we'll look at it in a second. So pause the video, don't be a cheater, and go through the shape, center, and spread. Okay, hopefully you should have a couple things written down like this. If you don't, let's add them, okay? Because with those values, you should have been able to answer a lot of these things. The first thing you should be able to notice is that this is right skewed, meaning that the majority of the data is on the left, okay? The second thing, I guess that's not a good picture, is that it is bimodal. So you would say that it goes up, and then it comes back down, okay? The center, if you looked at the observations, it said that the median was 15. Well, I don't know if the observations told you that. Yes, it did. The median was 15, and the mean, or x bar, remember that the mean and x bar are the same thing, was 16. But since this is skewed, and we kind of have talked about this, since your data is skewed, it is better to use a median. So you would say that the center, you would use 15 as the center, which would be, there's your center. Okay, the spread, because of the skewness, we use IQR instead, their interquartile range instead of your range. And we use it more than standard deviation because that is affected by outliers too. But in the measurements, it told us that Q1 was 11 and Q3 was 17, so your IQR is 6. Using your IQR, you can tell me what outliers are by using the 1.5 times IQR rule. Okay, we go through it, and we figure out that 1.5 times IQR, or 1.5 times 6, okay, gives us 9. So we take Q1 and we minus 9, so anything lower than 2 would be an outlier, and then we do Q3 plus 9, and that's 26. So that tells us 27, 35, 38, and 40. There are 4 outliers. These 4 right here are technically outliers. Okay? But I just want you to remember that shape, because we're going to go back to this situation. We're going to keep talking about these students who are guessing in meters. Okay? And they guessed in meters, and guess what? They were wrong. The room was actually 13 meters wide. So they all had some error. And their error is their guess minus 13. So what we're going to do is we're going to then distribute their error, which means we're going to take all of their guesses and we're going to subtract 13 from them. And what I want you to notice is this top one is the error graph. Okay, and the bottom one was their guesses. And I want you to notice that the shape, okay, the shape stays the same. Okay, the standard deviation stays the same. Okay, the IQR stayed the same and the range stayed the same. So the spread and the shape didn't change. We just shifted everything over 13 spots. These are 13 apart. These are 13 apart. All of these are 13 apart. Okay? This mean is 13 apart, but nothing else changed with spread and with shape. Okay? So in general, there's going to be a rule for that. The effect of adding or subtracting a constant. When you add the same number, A, or subtract, okay, adding A measures of center and adds A to the measure of center and location. So it changes your center and your location of things. But it does not change the shape or the distribution or measures of spread. Okay? So adding something is going to change location. Okay? But it's not going to change shape or spread. So you need to make sure that you have that down. Okay? The second thing, we're going to go back to this same example, is just like us, we probably don't understand meters very well. Okay, so it would not be helpful. It says, because of the group of Australian students is having some difficulty with the metric system, it may not be helpful to tell them that their guesses tended to be about 2 to 3 meters too high. Let's convert the error data to feet before we report back to them. So here's the error data that we just talked about. Okay, but that's in meters. And then we changed it to feet. What do you notice? Okay, looking at the error data, this is the top graph, and then this is the bottom graph. What do you notice about the statistical measures that we found? Okay, it said there are roughly 3.28 feet in a meter. If we look at it, what has changed? Okay, this time, if we look at the relationship between the two, I bet if you grabbed your calculator and you multiplied every measurement, okay, by that conversion, 3.28, that's the difference between the two. So in general, we have this rule that when we multiply or divide, okay, multiplying each observation by the same number B, so we do it by the same number, like our conversions, okay, our measures of center and location multiply by B. It also multiplies our measure of spread, okay, but it does not change the shape or distribution. So that's the biggest thing we need to remember, okay. And you guys, that's it for today. That's the lesson for today. So go ahead and get started on your homework. If you need more examples, there are more examples in your book. Okay. They start on about page, let's see, 85. Okay? Feel free to look through it. I think you've got this. Don't make it more complicated, and then look back on your notes.